Right, so everyone, we are all here, so I think we can get started. Okay, so I think the first thing I would like to mention is you guys probably have all received this email. So starting from today, for the lecture, we are going to meet online only. Okay, you probably know this already, but I just want to re-emphasize on this item here. All right. Um, so but for the lecture, for the lab part, you guys still meet in lab, in person, okay? So lab is still in person. All right. So another reminder will be the homework aid will be due tomorrow, okay? So make sure you actually get a chance to finish your homework by tomorrow midnight, okay? Still due by tomorrow midnight, okay? All right. So today we're going to be still checking on chapter 10. Yeah. Yes. Last thing I would like to mention. So since I'm staying home today, um, so so at the beginning of semester, whenever I was at home delivering a lecture, so a couple of times I was having unstable internet. So if that still happens today, just wait online until I get back. I should be able to get back. Okay. But if that happens, hopefully that's not the case. All right, so let's take a look on what we learned last time. Okay, so last time we pretty much learned the moment of inertia. So, and then the rotational kinetic energy. So for moment of inertia, for a point mass, if you have a point mass here, and then rotating with x rotation r away, then the moment of inertia is mr squared. Okay, so for a single point mass is mr squared. The kinetic energy would be then 1/2 moment of inertia omega squared. All right. So moment of inertia is expressed in the symbol of I. If you have several point masses, then you'll be doing summation of mj rj squared. So the mass of each object times the distance of the mass to x rotation. Okay, each of them, and then doing summation. All right. Now for regular shape objects, you can find the moment of inertia on this figure table here. Okay, if it's not given by a problem, but you can look it up. And moment of inertia also actually depends on where's the x rotation. Okay, so if you have different x rotation, then chances are you are likely to have different moment of inertia. Okay. For this, for continuous distribution of mass, not point mass, for example, if you have an irregular shape, and then also this applies to regular shape object as well. So you can do integration, okay? Integration of r squared times dm. So that means you are taking a small part of the object, and then that mass dm times the r squared. R will be the distance from the that small mass to the x rotation. Okay, and then integrating through the body of the object, they will give you moment of inertia of the object with the x rotation. Okay. You can also use a parallel axis theorem. So in this case, if the center of mass for moment of inertia of center of mass is known, then if you have another x rotation that is parallel to the original x rotation going through the center of mass, then it should be equal to moment initial at the center of mass plus md squared, where m is the total mass and then d is the distance between these two axes of rotations. Okay. All right, so that's parallel axis theorem. And then we took a look at several examples last time on how to do that. Today we are going to move on. So again, will be the analog to what we learned in linear motion. So in linear motion, we learn about the position, velocity, acceleration, and then force. Okay, so force would be like that is the dynamic, the driving force for an object that is moving. That, yeah, force is the cause of the object to be moving. So in this case, in the rotational motion, then we'll be looking at what's the cause of the rotational motion. Okay, so we'll start with the linear motion, and for the Newton second law, F equal to m times r, m times a acceleration. So then linear oscillation in relation to angular oscillation alpha, A is equal to R times alpha. So then force is equal to MR times alpha, okay? Now, we are going to intentionally make that the right-hand equation has similar form as the linear motion for rotational motion. So we are going to multiply R on the right-hand side here. That means on the left-hand side, you also want to multiply by R. So then on the right-hand side here, you will have MR squared times alpha, okay, which MR squared is I, the moment of inertia, that is the analog to the mass in linear motion, okay. So then on the right-hand side, you have I times alpha. On the left-hand side, you have R times F, okay? So then this would be the second law for rotational motion. So then on the left-hand side, we will call this new quantity as the torque. It's expressed in symbol tau. This guy looks like a T, but it's called tau. That's equal to R times F, okay, for the magnitude-wise, okay? So then torque is the cause for an object to rotate. Okay, so torque makes the object rotating. So if you exert force, then as a result, there's a torque on the wheel here that will make this wheel rotate. Okay. Torque is actually also a vector quantity. So for the magnitude, it's R times F. Okay. If in the case that R and F are perpendicular to each other. In general, R and F might not be, or in many cases, they are not perpendicular to each other. Then for the magnitude-wise, it's R times F times sine theta. Okay. So theta is the angle between R and an F, these two vectors. Okay. Now, this is a vector form, so actually the direction of tau is determined by cross product for R vector and F vector. You can use right-hand rule to determine the direction, okay? We'll be focusing on the magnitude today here. All right, so then for Newton's second law in rotational motion, it can be written as tau, the torque equals to moment of initial I times alpha, okay? So the derivative is listed, or derivation is listed up here. Okay, so this is what you have. This is for a single point object. Okay, so if you have several point objects in the system, then simply you'll be doing summation of the torques. Okay, or I'm sorry, if there are multiple forces on the object, then the result will be giving you multiple torques. Okay, so then if you sum up all the multiple torques, that will give you the moment of inertia times alpha, okay, for the system. So if in the system there are multiple forces, you'll sum up all the torques, okay. So then summation of torque equals to I times alpha, just like summation of force equals to I times alpha, or mass times acceleration when we talk about linear motion, okay. So again, similar expression, okay, just different names. All right, and then this it's a vector, torque is a vector, so you probably will be expressing in vector form, okay? If you are not just looking for the magnitude. So we'll take a look on one example here to start with. So this one says a 2.85 kilogram bucket is attached to a rope wrapped around a disc-shaped pulley of radius of 0.121 meters and mass of 0.724 kilograms. If the bucket is allowed to fall, what's its linear oscillation? And then what's the angular oscillation of the pulley? And how far does the bucket drop in 1.50 second? Okay. Now, when we are in linear motion, I mentioned that unless otherwise specified, the disk or the pulley that is in the system, we will treat it as an ideal pulley, okay? But in this case, it actually specifies the radius and then the mass. So the mass is not negligible, it's 0.742 kilogram. So in this case, then the pulley is not an ideal pulley. So we will have to consider also the kinematics of the pulley as well here, okay? So let me you guys start with a sketch over here to represent the problem. Again, if my view on your end, my video view on your end is small, you probably want to put in the speaker view. Okay, and then you can actually make the video on my end like larger in a larger window. Okay, so that might be giving a better visual. All right, so this is all we have. There's a pulley. Okay, non-ideal pulley, probably something like this. All right, it gives us the radius. Now, it's not perfect circle, but it gives you an idea. Okay, so radius, and then the mass is 0.742. Okay, I'm going to call this as small mass. Okay, the bucket, I'm going to call it a larger mass. It's probably a larger mass here for the bucket. So this is 2.85 kilogram. This guy's 0.742 kilogram. The radius is 0.121 meters. Okay, so it says what's the linear oscillation. Okay, so for this problem, for the bucket, okay, it's going to be like having a linear motion only. Okay, now for the pulley, it's going to have rotational motion. All right, so in this case, you'll be looking at the like the linear motion for this guy and then rotational motion for this guy. So separate. So this is rotational motion. Okay, this is linear motion. Okay. Now for linear motion on this guy here, let's draw the free body diagram. So there's a weight, mg or capital Mg. Okay, because the bucket is capital M. There will be tension T. Okay. Now on this guy here, you'll just have tension T here, right? All right, and then you might be thinking about the supporting force over here, but it actually, for rotational motion, when you write out the Newton's second law, okay, so you'll be writing out the torque, net torque, equals to I times alpha. For this guy, linear motion, you'll write out net force equal to mass times acceleration, right? So there's like the weight of this guy, mg. Let me use the red pen here. That's this guy mg. There should be supporting force. Let's call it normal force. So these two should cancel out. Okay. And or if you are looking at the torque, because the x rotation is where the force is exerting at, so then R for these two forces are 0. Okay, so then the torque by these two forces, it will be 0. Okay, because torque is equal to R times the force. In this case, the force is in this direction. This is the R. Okay, it's perpendicular to this guy. So on the disk, you can write that torque should be equal to R times T equals to I of disk times alpha. Okay, so this equation you can write. Let me call it first equation. On the linear motion part here, you will write the net force equal to ma. So then mg minus t. So mg should be larger than t. So then this guy will oscillate downward, right? So capital Mg minus t then equals to m times a. Okay, so this is the second equation you can write. Now there's a third equation because the pulley and the bucket are connected. So these are connected body. Okay, so then if this guy have oscillation going down here, then oscillation over here, alpha, angular oscillation, and then this tangential oscillation. So the oscillation of this guy should be the same as the oscillation for the rope at this point, right? So it will be the same as the linear or translational oscillation of this pulley here. So you can write that A equals to R times alpha. So this is the third equation you can write. Okay, so you have three equations here. All right. Now you have three equations. We will see that how many unknowns we have here. Okay, so you have actually T as the unknown, right? Tension is an unknown. alpha is an unknown, angular oscillation is unknown, and then oscillation is an unknown, okay? And the rest, the R, you know it, the capital M, you know it, G, you know it, small m, you know it, okay? So the rest quantities here are known. So with 3 equations and 3 unknowns, you should be able to solve for all of the 3 unknowns, okay? And then basically, you can have A and B. So the linear oscillation, that will be the A, and then the angular oscillation, that will be alpha, okay? And then for C, it's asking you how far does the bucket drop in 1.50. So part C is purely just linear motion, okay? So I think I have the equation set up. I will have you guys try to solve for this those 3 parts, okay? And then we can take a look on the solution in a few minutes together. I forgot to mention for the moment of inertia for the disk, this you can treat as a known because you can look it up for the disk. Uniform disk moment of inertia should be 1/2 of its mass times the radius squared. Okay, so then that's known here. All right, I think I saw a couple responses. So let's take a look at the solutions together, okay? So we have three equations, and then we have three unknowns, so we should be able to solve them, okay? Now, part A is asking us for what's the oscillation. So let's see if we can figure out the oscillation here, okay? As I said, this I is equal to 1/2 mr squared, okay? So you can actually, I think we can start with these two equations over here, all right? So we can eliminate the t, all right, and then alpha, because you can write actually a in this form. So a is equal to, or you can say, we can rewrite alpha as oscillation divided by r, okay? And then in this case, we can write t as I times alpha divided by r. Now I is 1/2 mr squared, so this is 1/2 mr squared over r, okay? So then r, I will cancel the square. This is mr over 2, okay? T is equal to mr over 2 then. All right. So and then there's times alpha. Sorry, missing alpha. So times alpha times alpha. Okay. So from here you can actually there's no space up there, but let's move it down here. So T is equal to mr alpha divided by 2. Okay. Now r times alpha actually is a, the oscillation, right, from there. So you can see the relation there. So then this is equal to MA over 2, basically. Okay, so tension is equal to MA over 2. Then you can substitute the tension in the second equation back. So like back and forth a few times. Go there. Then from the second equation, you can rewrite it as now capital Mg minus tension using MA over 2 to replace tension equals to MA. Okay. So then, let me see. All right. Let me see about the signs here. Okay, I think so. Mg minus tension is 1/2 a. Okay, I see the problem. Sorry about that. In the original, this one should be the capital M, okay, because that's for this guy. So that's capital M. Looking where it went wrong from my solution to here. So this is capital M then, okay. All right. So now we have this guy. We can move this to the other side of the equation, right? So then capital Mg that equals to capital M plus or times A plus small m over 2 times A. So A is the common factor here. You can actually factor that out. So then that gives you capital M plus small m divided by 2 times oscillation equals to capital M over G, right? So then your oscillation will be equal to capital Mg divided by capital M plus small m over 2. Okay, so you can plug in the numbers now. 2.85 kilogram times 9.8 meters per second squared divided by 2.85 kilogram plus 0.742 divided by 2 kilogram. Okay, so that gives you your oscillation as 8.67 meters per second squared, right? So I think I saw one of you guys submit this answer, that's right. And then the other one has a different number, so might be because you That was my mistake to put this as small m. Okay. All right, but it's actually capital M there. Right, so this is on the oscillation, linear oscillation of the bucket. Okay, let me pause for a few seconds to see if you guys have question on this. All right, so if that's clear, then the next part will be easier because then you're looking for angular oscillation that should be equal to the linear oscillation divided by the radius. Okay, so 8.67 meters per second square divided by 0.121 meters. That would be roughly 71.7-ish radius per second square. Okay. Now, Passy is asking you, so in 1.5 seconds, how far does the bucket descend? Okay, so that's purely linear motion. So it's 1/2 AT squared because it starts from 0, from rest, right? So the distance traveled should be just 1/2 AT squared. So then 1/2 8.67 meters per second squared times 1.50 seconds squared, okay? That gives you roughly 9.75 meters, all right? So I think one answer I saw is about half of this one. Oh, actually, no, this is, yeah, that was right. So this is about 4.87-ish meters. Okay, so that was right. The one I saw was right because I forgot about the 1/2 in front. Okay. So if that's clear, we will then move to the next slide here. Okay. So then after Newton's second law of motion, then in linear motion, we talk about work and energy, right, and power, etc. So in this case, similarly, we'll talk about work and power for rotational motion. So starting from linear motion, again, the work is defined as force times the displacement, right, distance, and that was in one dimensional. But in rotational motion, the displacement should be the arc length over here. So let's take a look on here. If there's a force driving this disk, and then in whatever like amount of time, that the arc length is travel as the delta s. Okay, delta s is equal to r times theta. So then F times R times theta. Okay, F times R is the torque, right? So then work in linear motion or in rotational motion actually should be equal to torque times rotational displacement theta. Okay, so this will be similar to F times D, linear force times displacement, but this is rotational motion. So you use torque, the analog for force in linear motion, times the angular displacement theta. Okay, so that's work. Now for the power, that's defined as how fast the work is being done. So you are doing time derivative of the work, right? So then in the case of that, if tau, if the torque is constant, then you are doing tau times time derivative of the angular displacement, which will give you the angular speed. Okay, so then power in that case will be equal to torque times angular speed or angular velocity, just similar as when the linear motion work power is equal to force times angular velocity. Okay. All right, let's take a look on a quick example here. So this one says turning a doorknob through 0.25 of a revolution requires 0.14 joule of work. What's the torque required to turn a doorknob? Okay, so it tells you theta is 0.25, but that's in revolutions. You want to convert it into radians first, and then it tells you the work is 0.14 joules. So what will be the torque? Okay, work equals to torque times the theta. All right, I'll give you a couple of minutes and then we'll take a look at the solution together. All right, so looks like this one is a very simple one. I see a few responses here, but I'm going to just show you the solutions here. So work is 0.14 joules divided by 0.25 in revolution. That means you multiply by 2 pi, okay? So then that will give you, so that should be in radians or dimensionless. So that should give you 0.089 newtons times meter. That's the unit, SI unit for torque, okay? So this one is pretty simple, okay? All right. So let's move on here. So next we are going to check on the work energy theorem in rotational motion, just like when we did for linear motion, we check on work and power, and then we look at the work and energy theorem. So again, this will be the similar algebra. So, but we start from the equation of motion for one of the equation there. So final angular velocity equals to initial angular velocity plus twice of angular acceleration times the angular displacement. Okay. And then also using the Newton's second law for rotational motion here, torque equal to moment initial times alpha. So then you rewrite alpha as torque divided by moment of inertia. Now doing substitution in the first equation over here, that becomes the third equation over here. So omega squared equals to omega 0 squared plus 2 tau divided by I times theta. Okay. Now from here, you multiply both sides by I, moment of initial, and then divide both sides by 2 to get rid of this guy. So then you end up with 1/2. So basically, let me show you the couple algebras missing here. So basically, from omega squared equal to omega 0 squared plus 2I or 2 tau over I times theta. Okay, so you're going to multiply each term by I, and then here by I to get rid of the I here. So then it's I omega squared equals to I. You distribute into here and then into there, omega 0 squared, right? Plus 2 tau times theta. Then you divide by or multiply both sides by 1/2. Okay, so 1/2. So then you have 1/2 I omega squared equals to 1/2. Again, 1/2 goes there, 1/2 goes there. I omega 0 squared plus 1/2 times 2, that goes away, cancel out. Okay, then move this guy over. So then 1/2 I omega squared minus 1/2 I omega 0 squared equals to tau over times theta. So this is the work, right? And then this is the kinetic energy change, right? Rotational kinetic energy change. Okay. So then this is the work energy theorem. Okay. So the same as what we have in linear motion. So basically, work done equals to the kinetic energy change. Okay. All right. So it's basically this guy here. All right. So work done equals to change in kinetic energy delta K. All right. Um, so if you have like multiple torques, okay, or if the torque actually is varying, then you will have to do integration. Okay, so net torque, if net torque is varying, again with the theta, then you'll be doing integration from initial angle to the final angle, or initial angular position to the final angular position in that way. Okay. And that usually we involving in the varying forces as well. Okay. All right. So let me see. All right. So I think this is a little bit ahead of um, the next chapter. So in sometimes you will see that the object is moving, is rolling, or actually it's like it's having linear motion and then rotational motion at the same time. So for example, when you are driving your car, the tires are rolling, are moving, are having rotational motion about the axis going through the tires, right? And then at the same time, the linear position of the tire actually moves with time as well. So for one moment, it's at a particular position, and then the next time, like a few times, next like delta t time later, it's in another position, right? So it has also linear motion there. So if that's the case, so usually like if you have wheel that's rolling, or the bicycle wheel or tire wheel, etc., or maybe a sphere that rolls down, uh, um, like inclined surface or slope, then at the same time you have rotational motion and linear motion on the object. So in that case, then the kinetic energy of the object should be coming from both the rotational motion or rotational kinetic energy and then linear kinetic energy. Okay, so the total kinetic energy should be equal to 1/2 mv squared. V is a linear speed or linear velocity, and then plus 1/2 I omega squared. I is the moment of inertia, omega is the angular velocity or angular speed. Okay, and if the object rolls without skipping or slipping, so that means it's the at the contact of point, it's actually having like when the wheel is in contact with the floor. Okay, so it's not slipping. That's the case when it's rolling. Okay, so then in that case, angular velocity and linear velocity actually have relationship there. So V is equal to omega divided by R. Okay, so then omega can be rewritten as V over R. So in that case, it's going to be 1/2 I times V over R. Now you can see for the mass, for the moment of initial, okay, so in this guy, for this guy, you can rewrite. So if you single out 1/2 mv squared, then it becomes 1/2 mv squared times 1 plus IMR squared. Okay, so you can see m cancel out, so it will be 1/2 I v over r squared. Okay, so then this is the total kinetic energy for an object that is rolling. Okay, meaning it's having linear motion and then the rotational motion at the same time. Okay, So you can see the total kinetic energy is a multiples of its linear kinetic energy, right? So this guy multiplied by a factor here, which is 1 plus the moment of inertia divided by mr squared, okay? All right. Let's take a look on an example here. So this one says, if you have two masses, so this is an Atwood machine, okay? Two masses here, M1, M2, and M1 is 5, M2 is 3 kilograms. They are released from rest with M1 at the height of 0.75. So this H is 0.75 meters above the floor. When M1 hits the ground, its speed is 1.8 meters per second. Assuming that the pulley is a uniform disk with radius of 12 centimeter, find the mass of the pulley. Okay, so let's take a look here. So this one says find the mass of the pulley. So that indicates the pulley is not an ideal pulley. You need to find its mass. Okay, it's not massless. So M1 here, M2, and then this H, 0.75 meters. M1 is 5 kg, M2 is 3 kg. Okay. Now, what would be the mass of this guy? Let's call it capital M. Okay. And then the radius, let's call it R. That would be, it says it's 12 centimeters, so that means 0.12 meters. Okay, just convert it into that. Now, the moment of inertia for the disk should be equal to 1/2. It's a disk, so mr squared. Okay, so that's something you can write out over there. So now let's examine the scenario here. So you release the two weights. So this one is heavier, so it's going to descend, and then it will hit this guy. Okay, so this then for the final status, M1 is on the floor here. M2 should be somewhere up here, right? M2, and then if M1 drops 0.75, this one will ascend by 0.75, right? So the 0.75 meters there. Okay. Now you can see that this guy drops down, this guy goes up. So that's change in potential energy of the two masses. Okay. So basically, we can actually utilize conservation of energy over here, right? Because the only force that's doing work is the gravitational force. Okay, so on this side, on both sides there. And then for the tension wise, the tension going this this direction, there's tension on this direction. Okay. So then work on by the tension on this disk, they should cancel out. So that shouldn't play a factor here. Okay, so work is only done by gravitational force here. All right. So you can apply conservation of energy, conservation of mechanical energy. So initially, for the initial status, the kinetic energy should be 0. Initial kinetic energy should be 0 because initial is from rest, right? So Ki plus Ui is equal to Kf plus Uf, all right? Ki 0 plus, okay, we are going to take this as the ground level of potential energy. So then M2G H will be, for M2 will be 0 plus M1GH, okay, H will be that guy, the 0.75. All right, now for this one, for the pulley, you can say capital MG, capital H. You can say this, the height is H, okay, capital H. It doesn't matter because potential energy of the pulley initial and final should be canceling out each other. Okay. Now for the kinetic energy final, you'll have 1/2 m1v1 square plus 1/2 m2v square. Or let's just use v stands for final because they are connected, so they should have the same v. So 1/2 m1v square, 1/2 m2v square, and then plus this disk is rotating, so 1/2 I omega square. Now omega and v should have a relationship of v over r equal to omega. Okay, so we can also express that in that form. Plus for the potential energy of the three objects. So m2g now this time should be h above the ground level plus m1 should be 0, right? M1 should be now at the ground level plus the disk mg capital H. So again, as I mentioned, that would cancel out that, so it doesn't matter really. Let me stop sharing, maybe you can see a better view of the camera view on my side. Okay, so you pretty much, so this is 0, so this one goes away, and then this is 0, that one goes away. So you pretty much will have just one term remaining from the left hand side, m1gh, okay, equals to, on the right hand side will be 1/2 m1 plus m2. You can put these two together, 1/2, okay, and then v square, and then plus 1/2 now capital M r square times v over r square, right? The omega is equal to v times r, and then the I is equal to that guy, 1/2 m r square. Okay, so that's I, or actually that's 1/2 here, 1/2, this is I omega square. Okay, so 1/2 there, plus m2gh. Okay, so here if you square, so this becomes v square over r square, right? So then r square and then this r square should cancel out. Okay, so you would have 1/2 here and then v square there, now 1/2 capital M. So you can put that together. You can single out 1/2 and v square, so 1/2 and v square, so that equals to 1/2 small m1 plus small m2 plus 1/2 capital M. Okay, v square plus m2gh. So this is what you have after you apply conservation of energy here. All right, now let's see what we are looking for. We are looking for this guy, capital M. Okay, and I think the rest, we know the rest of the quantities in the equation, so we should be able to solve for that. Okay, m1, m2 are given. G is the 9.8, H is the 0.75, so we have everything. So we'll move this guy to the other side of the equation first. So then that becomes m1 minus m2 times gh, because both terms has gh, okay, equals to 1/2 m1 plus m2 plus 1/2 capital M v square. All right, you can multiply both sides by 2 to get rid of 1/2. All right, now you're looking for this guy, so you'll divide v square first from the both sides. V square. Okay, get rid of that v square on the end. Okay. Then now on the right hand side you have m1 plus m2, right? Plus 1/2 capital M. You are looking for capital M, so you'll move this to the other side of the equation. Then that tells you 2 times m1 minus m2 gh over v square minus m1 plus m2, right? Move this to the other side of the equation. Then you have just 1/2 capital M remaining on the other side. Now multiply it by 2. So this multiplied by 2. So then you'll have 4 times m1 minus m2 gh divided by v square minus 2 times m1 plus m2. that equals to your capital M. Okay. All right. Now you can plug in all the numbers you have or given by the problem and then solve for your capital M. So 4 times 5 minus 3, I'm going to just leave the units out because I have everything in SI units. So my final answer should be in SI unit. Okay. Divided by V square would be the 1.8 meter square minus twice of 5 plus 3. Okay. So if you plug in everything correctly, this should be about roughly 2.15 kilograms. Okay. So that's your capital M. All right. Questions you guys might have? Okay, so if not, we'll stop here for today. So remember, from tomorrow until next Monday, we all meet online, okay, for the lecture part. But you still go to the lab for in-person lab activity, okay? So see you guys tomorrow.